Uh, Perfect. So, welcome again. So, obviously, last week you had lots of fun, lots of sport activities. We were here only in limited numbers, basically me and Robert. Uh, and today we will continue. So I want to finish the elections topic, and I would love to encourage everybody to take part in the super elections, where we electing the best superhero. Uh, some of you have participated already. Some of you did not. So the table is in the comments section behind the meeting. And so please, if you haven't voted yet, please do so. It's super fun, and I want you to spend some time playing with the table of results. So let me start. I created a static snapshot of the elections right after Gabi actually participated. And thanks a lot. I see some people are voting. One more comment before I start. I try to share the sheet with you. So on sheet one, you have the table where you should express your votes. Uh, and Perfect, Robert. Thanks a lot for being a valuable part of the community. And I have one, and I added sheet two for now, which is just a static snapshot, and I want to tell you something about it. But before we start, I have a message for Hamza. Do we have Hamza here? Uh, the important thing, if you look at Hamza's voting, so Hamza obviously could not decide between Wonder Woman and Xena, and between Spider-Man and Batman. So in his preferences, these are not linearly ordered. So my I would love, Hamza, if you reconsider and decide and provide a linear ordering. So I understand that Wonder Woman, Xena, it's difficult to choose. The example voter also had to choose somehow, because we need a linear ordering. So I put here I put Hamza in red for now. Uh, so he changes his preferences to be a linear ordering. So the interesting thing I want to comment on today is the partial results, and the way how we actually count it. I did it in Excel. So when I transferred it to Google Sheets back, it's just static snapshot. I'll try to do it somehow, maybe share the Excel table with you as well. But let's switch to sheet one and comment on what happened. You see that we have a static snapshot right after Gabi participated. And now let's take a look at this table uh, on the top right, where we actually see the counts of the positions for individual heroes, right? So for Batman, we have the first position, and he was four times the first one, right? The Spider-Man as well, four times the first one. Uh, right before Gabi participated, Gabi's most favorite is Spider-Man. Actually, we had a majority winner, the Batman, because Spider-Man had only three. But after Gabi's vote, we have a tie. Actually, right? We have Batman and Spider-Man both achieving the highest number of the first places. And then for Batman, you see that he was on the second place twice, on the third place twice, on the fourth place 3 times. Nobody put him on a fifth place, and one person did not like Batman at all, and so on. So you have the position. Superman was never the first one. Wonder Woman was twice the first one, and so on and so on. So this is basically what you deduce just by counting the positions uh, and putting them into a table. Thank you, Robert. Now, actually, we're getting to the point that the elections are no longer valid, really, right? Because when we see the other choices, we can start voting strategically. But what can we do, right? Uh, yeah, so it's sort of interesting to see that we actually have a nice distribution. The opinions vary a lot, and so the interesting thing is if you see the table just from the point of view the positions. So we already have a tie right now, right? Maybe after the after other votes it will be different, but even if we did not have a tie, and for example Batman would get 5 votes, then still if you count the first positions for of other superheroes, it adds up to something like 10. So obviously, the Batman is not a majority winner. He did not achieve, the more than 50% of the candidates. Now, in this situation, in this snapshot, we even have like two guys being in a tie. So obviously, we see some of the properties of this. Majority based systems. It would be nice, and that's one of the things I would like you to play with the table, either do some like experiments. So obviously the runner off strategy would work. So for example, Batman and Spider-Man will go for the second round, and then people would vote only for these two. So we can simulate it. I'll try to prepare a table, or if you find a time to play with it, to try to take only Batman and Spider-Man into account and recount the votes for them, just to see what happens. So that's one thing I would like to see from the table and maybe play with it a bit. Another thing that's important is to try to do the board accounts that are supposed to be sort of taking not only the winners into account, but taking all the preferences into account, right? That's why we need the linear ordering of individual voters. So if I scroll here, take a look at the Q column where we have the board account. So the board account, if you remember from, well, it was 2 weeks ago, and you were playing football all the time in between. So I don't know if you remember, but the board account basically means that we're assigning points uh, to the rank, right? So for the first position, you get 5 points. For the second position, you get 4 points. For the third position, you as a candidate get 3 points, 2 points, 1 and 0 for the last position. So basically, we're recalculating for a Superman for whatever for Xena, we're taking these numbers in the column O, like 2 times at the first position, 1 times at the second position, 1 time at the third position, and so on. And we're basically computing a product, right? Uh, so we're computing 2 times 5, 1 times 4, 1 times 3, 2 times 2, 2 times 1, and 4 times 0, and adding it up, right? So In this table below, the first line, the line 13, actually tells us the Borda count for all the superheroes. And you see Batman has 40, Superman 24, Wonder Woman 23, 23, Spider-Man 39, Iron Man 36, Xena 23. So we have a Borda winner, a Batman, but you can see that it's really, really close, because Spider-Man's having 39, and so on. And then we have Superman, Wonder Woman, and Xena having the same board account, right? 23. So this is also quite interesting uh, to see how when we count the overall ordering with border system, uh, that that it sort of reflects the previous uh, ranking of the candidates, but uh, in a sort of in a different way, right? So this border is supposed to be sort of fair, because it linearly assigns points based on the ranking, right? We might think of some other scheme how to assign the points. So basically, the column R shows something different. It's like exponential board, where we're uh, trying to prioritize the better positions, right? So now the weights, the points we're assigning are not just a linear order of numbers like 5, 4, 3, 2, 1, 0, but they're exponential. So the last position gets 1 point, the one above gets 2 points, then 4 points, and so on. So winner in our case gets 32 points. So this is a very skewed distribution, and the results we see are on the second line of this table. So this is sort of exponential border, a different way how we assign points to the rankings, right? And the interesting thing is that we see that Batman is no longer a winner. So obviously, Batman and Spider-Man are sort of controversial figures. They have quite a lot of high rankings, but also some very low rankings. And so in this case, the Iron Man would be a winner, right? The Iron Man has lots of second positions. Ah, perfect. We have a common. It's a joke, Wawa. Thank you, Gabriela. Thanks a lot. Yeah. Let me see how you voted for Batman. Ah, yeah, you kind of like Batman. Perfect. Yeah. So, so we will see that by assigning different weights to candidates, that should prioritize the winner. That what we're actually getting is we're prioritizing the higher ranks, but because Batman and Spider-Man, who were fighting for the first position in sort of in the majority, plurality, and in standard linear border count, now are going down because they're controversial figures, I guess. And the Iron Man, who was only once at the first position but has lots of second and third positions, is winning. So that's really interesting. Sometimes people consider different weights for different positions. So this is extreme, the exponential weights, but you can see that by assigning weights to the ranks, you can totally change the position, right? One last thing I wanted to do to sort of simulate. Uh, there is this figure in Czech Republic called Karel Janeček, Uh, he actually studied Faculty of Mathematics and Physics, right? And he became rich uh, by exploiting those micro transactions uh, in the share market. And he's now sort of a public figure. On one hand, a donator of money to research. So he's one of the guys who's putting money into the so-called Neuron Foundation, and that's actually very nice of him. And the whole Neuron Foundation is doing a lot for support of the science and popularization of the science. So he has good parts. And also more of a controversial parts. I think that he's pursuing some controversial ideas nowadays with the pandemic situation. He's one of the guys from the camp of let the virus sort of exist in the society. We want freedom. I don't care if some old people die, and so on and so on. He has also proposed a voting system that I tried to simulate a bit, but it's not exact simulation, because the simulation would require to uh, the different voting system, not assigning the ranks like this, but he calls it elections 2.0. Now he has a version called 2.1. So that's the S column of the D21-ish. And so his idea is that when you're voting, you're not required to provide the complete ordering of the candidates, but you have the positive votes and negative votes. And so what you can do is you have to put twice more, two times more positive votes than negative votes, but you are allowed to vote negatively as well. So you can put some positive votes for your favorite candidate, uh, more than one candidate, but you also have like a -1 point that you can assign to a candidate that you really hate. And the idea is that you have to use two times more positive votes than negative votes, but it's possible. I tried to simulate it a bit just by border count with the weights that are going into negative. So what you see in the column, the D29-ish, 21-ish, sorry, is that what I did, I just shifted it. So the first candidate gets 4 points, the last candidate gets -1 point. And the results of this type of election we have in this column, and you see it changes the situation again. So what we did is we sort of emulated the situation where the one the last candidate of your choice is actually getting negative voice. uh, and it's interesting that here we have still the linear ordering. So we have 4, 3, 2, 1, only going to negative numbers, right? So being last now, so the exponential part was trying to express that being the first or second, as we've seen, is really important, right? It resulted in a situation in our voting that the guy who actually was not the first choice for majority of the people, but has got lots of second and third positions, climbed up to the first overall position, right? The Janacek system saying if you're the last option for a candidate, you sort of suck, and so you're getting -point, only one -point, right? Other than that, we only shifted the border count coefficients, right? So instead of 5, the first one is getting 4, but the importance that the last one is getting -1 nothing special, is totally changing the thing. The scores are now really low. We see that now the winner would be a Superman, right? Totally different situation than before. So obviously, this means that Superman is not getting lower scores like the last position and the one above, the fifth position, is somewhere in the middle, but by punishing candidates to being the last option for uh, more voters, we're getting totally different scores. So now the Superman would be a winner because he's probably the least controversial figure, I guess, right? Batman and Spider-Man are sort of pretty low. Iron Man is quite high. So Iron Man is steadily occupating sort of upper middle positions, right? So it's really interesting how just changing the weights for the orderings, you're getting totally different winners, right? Are they? Jakub is saying that the numbers for the accounted back. Uh, yeah, I don't have the Excel table here, so let me think. Feels wrong. Okay. Let me check. Let me check. What what did I do? Maybe I did the computation wrong in my Excel. Uh, but yeah, yeah. Well, Spider-Man gets 1-0. Uh-huh. Yeah, it doesn't feel right. You're right. So I will double check it and then I will publish the Excel sheet so you can play with it. Yeah. Yeah. It seems that something's wrong here. Yeah, I will double check. Uh, okay. So we will see the results for this. Uh, Nevertheless, the point is that really it's difficult. Uh, yeah. So I will publish version 2.0 of my Excel spreadsheet after the talk. Hopefully less bugs. But nevertheless, the point is that the counting systems are really important, and you get totally different orderings based on the system. That's why people are still sort of trying to find uh, ideal method, the combinations of methods, and so on. We were discussing that there are some combinations with Borda, right, where you do it the Condorcet way, the majority of plurality. Uh, we have with board accounts and so on. So we have another. Uh, yeah, uh, yeah. Jakub is asking. Well, if you go to minus points, I will do the experiment and then publish the table afterwards. Yeah. it's not, and again, it's not like a proper implementation of what Karel Janeček is actually proposing. The people who are playing with the minus points, it makes sense to do it that you gather the points during the voting, right? Okay, so so we'll get back to this, and yeah, exactly, Robert. I will try it, something like that. Yeah, yeah. You have two, yeah, you have two positions that you're getting. Yeah, yeah. You have two positions. You're getting your ones, and you have the last position is a sucker, and then in between the zeros. Yeah. Uh-huh. Uh-huh. Thanks a lot. Thanks a lot. That sounds more reasonable, and I will try it. Yeah. Great. So, so what I would like to do next in the talk is that we will the most important theoretical property is the so-called Arrow's theorem. I would like to talk about it for some time, and then just let you to play with the table more, so we can or you can by yourself try some of the properties. So what we have demonstrated is that different countings from majority, plurality, sort of the Condorcet way, and border countings can produce different winners. And sometimes it's difficult for our situation. Even with those, this would mean we choose Batman and Spider-Man going to the second round, and then we can try what happens when we will do the fight between those, right? So so this shows that that the system, the voting system, the voting procedure really matters. And there was a mathematician called Arrow who tried to study the properties and of the voting system, and he proposed four uh, basic properties that should work for all systems, and then studied if they are satisfied in some of the systems we were discussing. And the Arrow's theorem is the result, and it actually is quite negative. In a way, it says that these four properties never hold together. So let's take a look at the properties, and I will try to describe them and then express the Arrow's theorem, comment on it, and then we can return back to the table and try to play with it more uh, if we see some of these properties to being satisfied or violated. So uh, so when Arrow tried to study the properties, some of the properties are quite nice, and one of the properties that sort of we should think like very reasonable is the so-called Pareto property. Pareto property. Uh, so the Pareto property, which we know what the Pareto principle means, right? We are trying to optimize more things together. So we're like a multi-objective. We're doing multi-objective optimization, and the Pareto front, the Pareto winners, the Pareto candidates are those that are sort of on the border. So when we can see we're maximizing two things at once, then we have the Pareto candidates are here, right? The Pareto border is here. So we are saying they're Pareto dominating, meaning that if we change the position of the guy and move it, then either this way or this way, we're violating the condition. He's no longer optimal. So he or she cannot do better than being here. So that's the principle of Pareto approach, right? And the Pareto property of the no. The Pareto property of the elections can be expressed very easily. We're trying to say if everybody prefers uh, Coca-Cola to Fanta, then the result of the voting procedure should also be that Coca-Cola is better than Fanta, right? So so if all voters would prefer, I don't know, Superman, if in all votes Superman is higher than uh, Batman for all, then it should be true that the overall result is that Superman is better. The social welfare, the overall thing, also says Superman is better than Batman. Uh, well, this sounds very reasonable, and it's actually true for majority uh, and for board account. So majority and Borda satisfy these. But some of the systems we were describing in the previous lecture uh, do not satisfy this. For example, the sequential majority systems, sequential majority, where you're playing sort of pairwise tournaments and the winner moves further. These systems do not satisfy this, right? So the obvious property that's sort of the Pareto that should be the main principle, but it's very strict. It's saying if you have something that holds for all, some ordering of candidates, it should be satisfied in the final outcome, right? So some of the systems that were created to sort of speed up the procedure, like the tournament type of the systems, they do not satisfy the Pareto property. Okay, uh, so that's one property, and very reasonable, makes sense, satisfied if if the majority and Borda systems satisfy this, so they would not violate. The another property that's sort of a strong property is the property of the Condorcet winner. We know that the Condorcet winner is such a candidate that beats the opponents in pairwise comparisons, right? So if you consider all pairwise comparisons of the candidates, the Condorcet winner is the one that beats all the opponents. And the Condorcet winner condition is that the if you have the Condorcet winner, is the overall winner of the elections, right? So so to be a Condorcet winner is actually very strong conditions. in many cases, we don't have a Condorcet winner because the votes for the candidates are distributed in a way that that we cannot say this candidate is obviously the best one. There is an example in the last lecture in the slides where you have this sort of paper, stone and scissors, paper, rock and scissors situation where the voters are sort of the voters have sort of cyclic preferences, right? Something like that. You have three voters, three candidates, and they express their votes in a way that you have this. That's the Condorcet paradox, right? In this case, we do not have a Condorcet winner. They're sort of tied, and so we know that for more than two candidates, if we have three and more candidates, the Condorcet winner might not exist. The Condorcet winner condition for arrow is that if such a winner exists, she will be the overall winner. Well, the interesting thing is that, again, the Condorcet winner is a very strong condition. To be a Condorcet winner is a strong condition. The condition that the Condorcet winner is the overall winner in the social welfare function, in the aggregation of all the votes, holds for Borda, and it holds for sequential majority. So the tournament, that's why they're organizing tournaments in tennis, for example, right? They don't have time to play all the matches between all the candidates, but they are sure that the best one will win the tournament, right? So the tournament is the sequential majority type of voting is good for selecting the overall winner. But for example, the majority itself is not making sure that the Condorcet winner will be the overall winner. So another property that's important. So the Condorcet winner condition, the Condorcet winner is the overall winner, right? Quite strong, does not hold for some of the systems such as the majority. And another one that's important, and that's well, that's I think one of the important properties that's sort of difficult to verify actually, and it's also difficult to memorize. It's called independence of irrelevant alternatives. Independence of irrelevant alternatives. IIA, independence of irrelevant alternatives. Well, it is what it says. It says that that basically the outcome, if you have the outcome that says X is better in the elections than Y, so this outcome, this result, should depend only on relative rankings of X and Y in individual votings. So the fact that Batman is better than Spider-Man should depend only on relative vote orderings in votes. In other words, how you can violate this? Well, you can violate this that you have some other candidate, like a Z, and if you remove the candidate Z, or if you add some candidate W, it should not uh, be have any impact on the overall ordering of these X and Y's, right? So the voting scheme should be that the orders of X and Y in individual votes should aggregate to some result in the overall voting, and it should be totally independent on the ordering of other candidates, like adding some candidate, deleting some candidate should not impact the votes. Yeah. This sounds reasonable, right? I have strong opinions about Batman and Spider-Man, but what happens to Xena if Xena is there or is not there in the elections should not influence the overall position of Batman and Spider-Man. Well, this sounds very reasonable, but it's actually not true for most of the voting schemes. So not satisfied for majority, neither Borda, neither sequential majority. If you want to have something that satisfies the this independence of irrelevant alternatives, you need very careful voting scheme. So this, I mean, this sounds complicated, but in reality, it says sort of a simple thing that the overall ordering of two candidates should depend only on individual ordering of those two candidates and should not depend on the existence of other candidates in the ballot, right? So this one is important. And there are two more conditions. Well, the arrow theorem, you will find different formulations from 4 conditions to 7. So there are different versions, but these are important. These are the important properties. The Pareto optimality is really important. The Condorcet winner sometimes is excluded from the from the theorem, from some simple versions of the theorem, probably because being a Condorcet winner is a very strong property itself. Some conditions are trying to describe more social aspects of the voting systems. So one of those properties is called universality. Yeah, the universality property for us is not sort of a property that we can somehow manage, but it's important for the practical for the practical meaning of what elections are. So Robert, that's why we have 5 of them. But the universality, you will see that the universality says that basically the social welfare function, the outcome should depend on all votes in a uniform way. So we should take into account all individual preferences, and the social welfare will be constructed in a way that we are taking all individual votes into account. Right? So this might make sense for practical implementation of the elections. So, for example, the universality would not be true for elections in the 19th century and then the beginnings of 20th century, where some groups of people did not even have a right to vote, right? From women to I don't know, black people in the United States, and so on and so on. Right? So the universality is important to consider, but it only says that all votes should be taken into account. Right? So okay, so far we were saying let me reiterate. We were saying Pareto condition, right? If for all the voters Batman is better than Superman, it should be the same in the overall votings. Then we have the Condorcet. Condorcet winner is the sort of the super winner of the election. Condorcet winner is the one that would beat all other candidates in pairwise comparisons. The Condorcet condition is saying if there is a Condorcet winner, it should be the winner of the elections. Then we have the independence of irrelevant alternatives. That's the one that the ordering of two candidates in the result should depend only on relative orderings of those two candidates in individual votes. Right? That's the third one. Then we were saying that we have the universality. That's sort of a actually it's a good condition because you can think of having voting schemes that are saying, you know, let's cross out I don't know, some votes, like totally, right? But universality is saying each of the voters is submitting the preferences they should be treating in the same way, and so on. So for practical reasons, really important, and it's actually the universality of the voting procedure is considered one of the best things in democracy, basically, right? Uh, and the one property that's sort of really important, not because it's really important because that's how Arrow's theorem is sometimes formulated, and the property is called dictatorship. Dictatorship. So I will be talking about dictatorship. That's the last one of those 4 or 5 properties. The dictatorship is a system. Well, dictatorship is a system where the social outcome is determined by one of the voters. So the social outcome, the social welfare is actually the dictator's choice. So we have one of the voters that's called a dictator, and basically the system is taking his or her vote as the one that's the result that's been the social welfare. So so what we're usually saying this really means like you have a sort of super power voter, a kind of dictator that that assesses the result of the elections. So we can have a property of non-dictatorship, saying that that there is no dictator that actually is determining the social outcome of the elections. And now the Arrow's theorem says that we don't have a system. Arrow's theorem says that we don't have a system where these properties are satisfied together. So Arrow said that if you have 3 or more candidates, we've seen that for 2 candidates it's sort of easy, right? The plurality becomes majority, and so it's sort of easy. And of course, for 2 candidates, you don't have conditions like independence of irrelevant alternatives. There are no irrelevant alternatives, right? So the Arrow's theorem is saying for 3 or more candidates, no ranking system satisfied all of the universality, non-dictatorship, Pareto, and the independence of irrelevant alternatives. You can add the Condorcet winner condition there as well, really strong, but this is sort of even enough for those. So no ranking systems, if you have 3 or more candidates, satisfies all of these really reasonable, make it 4 conditions for how the elections should work out, right? So sometimes, why I'm saying that the dictatorship is important, because sometimes the Arrow's theorem is cited as for elections with more than 2 candidates, the only voting procedures satisfying the Pareto and independence of irrelevant alternatives is a dictatorship, where one of the voters is saying what the social outcome is, which sort of is true, that that you can put this into negation and saying, well, okay, so I have a dictatorship, and then the other are satisfied. It doesn't make much sense from the mathematical point of view or even practical point of view, but the fact that the non-dictatorship condition is there as well is for the general public and for the politicians and social scientists is the important thing. For us, probably the Pareto optimality, independence of irrelevant alternatives, is the ones that are interesting. The Condorcet winner should be a winner also. So also the Condorcet winner condition is interesting for us, because for us these mean sort of reasonable conditions for the voting system, right? So one of the if you see some of the YouTube lectures, the Pareto, they're saying, well, if every voter prefers vanilla ice cream uh, over chocolate, and then the elections turn out to say chocolate is better than plain vanilla, obviously people are not satisfied with this. The Condorcet winner should be a winner. If a system does not make sure that the Condorcet winner that would beat all the candidates in pairwise comparisons does not result in a winner, so this should also be considered something strange. But we will see that it's possible with the majority schemes. The independence of irrelevant alternatives, for some time, well, it's intuitive if you define it. It's counterintuitive how this can be violated, but it's actually pretty easy, and there are many examples that some irrelevant voter changes the relative positions of other voters. So that's one of the things we should try with the table again. So to conclude, uh, the uh, the Arrow's theorem is very important for the elections, and it's sort of a negative result that shows that all the properties that look very reasonable are not satisfied altogether in uh, any system in principle. So we should choose the system depending on what we want. Right? Maybe the Condorcet winner condition is not the one we are preferring, so maybe the strongest candidate can be outperformed by some other candidate that's more that's not the best one in the overall, but probably sort of like Iron Man in our example, uh, like pretty good, uh, but probably not the best one. But maybe Iron Man can end up being the overall winner. So that's violating the Condorcet condition. The Pareto optimality should be satisfied, but again, not all systems satisfy this. Like the sequential majority is violating Pareto because the idea of the sequential majority is tournaments, and so tournaments are fast in selecting the winner, but they do not do the fair assessment of the other candidates. Right? They are dependent on the order of the rounds where the candidates are pairwise compared. Right? So the pairwise comparison itself is the best thing you can do. But if you have more candidates and you're doing tournament, maybe the second best will be in the first round with the best, and then you know nothing about his relative position because the second best loses against the best. The best sort of bubbles in the tournament uh, to the top, but the second best just loses in the first round, and that's it, right? So this is how the Pareto property can be violated. So the Arrow's theorem is important. Is sort of a negative result. Uh, uh, People are saying that it basically says that there are some fundamental limits to democratic decision making that not all the nice properties of the decision-making process are satisfied. On the other hand, the thing with the dictatorship that's very catchy for general public should not be taken that seriously. There have been interpretations that the only working system in society is the dictatorship, and so it's not true. So although the Arrow's theorems showing us some limit of election procedures, still it's the best what we have, and we should think of different systems that satisfy the properties we value more, basically. Yeah. So so that's about the Arrow's theorem, and now I would pretty much end up the lecture. I would like you to play more with the elections. So let me see. Some other people voted. Let's. So I will try to check my Excel where I have the tables, and make them public. And so you take some time checking how the results are now. And one thing I would like you to consider is the property that's probably a bit of counterintuitive how this can happen, and it's the irrelevance of independence of irrelevant alternatives. And the way how you can check it usually is that what you do is you're looking for the potential candidate that would show us the violation, and the obvious candidate is the last one. So try to think about the scenario where you have the border, the standard border count. So we're considering this line basically, and what we're gonna do, we're trying to take a look at the last candidate, the loser. So hopefully after more votes we have somebody losing, like a Superman, I don't know, Superman. And then try to do the following: just pretend the Superman is not in the elections at all. So we're deleting Superman and recounting the border for the remaining candidates, and then check the position of the candidates before removing the Superman and after removing the Superman. And the relative position of the candidates should not change, right? If it does not changes, it means that the condition is satisfied for this particular case, right? Of course, we should, in order to check it, we should try to remove all the candidates. But the last one is actually the obvious choice how to test it, right? And if the relative ordering changes, then we see that the independence of irrelevant alternatives is not satisfied, right? So to make it clear, what we are trying to test in our table is that we have some ordering. So let me see what ordering we have. So imagine that we have an ordering saying Batman, and then Spider-Man, Iron Man, and then whatever, Wonder Woman, Superman, and Xena. for example, right? So that's the ordering. And then we decide to remove one of the candidates, say Zena, and we're looking if this will remain the same, right? And sometimes the effect of removing Xena might mean that, I don't know, Superman will move uh, much higher or something like that. Yeah. And that means that the independence of irrelevant alternatives is violated, right? Yeah. So that's one of the experiments I would like you to try to check, and because now we have lots of data, so we can try to experiment, and then next time we can spend 1 or 2 minutes just discussing if you have found something like that, and so on. So that's pretty much it. I will put the Excel link here, and so you can play with it in Excel, and I will repair my elections 2.1 to work actually. So that's it for today. And next time we have auctions. You did auctions with Martin, right? So we will check only the systems, the main results about the auctions, and I think that we will manage to do auctions in one lecture, even with some examples and everything. Uh, I'll try to also talk about more exotic versions of auctions. You probably try the English, Vickery, maybe Dutch, and so on. So I will again try to. Okay, I see some comments. Yeah, yeah. You have an auction homework, and well, perfect. So basically, next time we can make it more interactive, and you can tell us about your experience with the auction homework. Robert, even if you're frustrated, that's also good to know. So, and maybe you can find actually somebody here to help you with it. Perfect. Oh, and Robert was also, yeah, like U.S. presidential election, the Condorcet winner lost. Yeah, yeah. Well, that's probably a good point. Like we've seen a couple of different systems, right? And those are only considering uh, how you transfer the votes into some kind of ranking, right? And we've seen that even the border can have different versions and so on. And then usually in practice, the systems, how you assign either the winner or chairs in a parliament can be even more complicated. You've seen that in Czech we had recently a change of a law, right? Because first of all, you have the 5% threshold, and then the way how you recount the votes for the positions in the parliament was considered not fair because it actually preferred parties who got more votes, right? So, and the system, they are now trying to fine tune the system to make it more fair in this respect. And in the United States, the presidential election is a chapter on its own. It's complex, and also the basically the if you distribute the votes into different states and consider different weights for those who are actually voting for the president, then you can get those results that do not seem fair. That if you just consider the overall sum of the votes, one candidate would win, but because division into states and the system, how you accumulate the state votes can result in a fact that the guy who receives overall the sum of votes, the majority, does not win, right? So in practice, the systems are quite complex, and they do not have they do not satisfy this condition, right? For example. Yeah. Okay. That's the final remark. So it's been fun, and I hope you had fun with the super elections, and still try to think of the independence of irrelevant alternatives. I think it's important. So try to delete the one of the candidates and see if the ordering of the other candidates changes or not. And we will discuss it very briefly next time at the beginning. And I will put the Excel sheet, the repaired one, here in the chat. So thanks a lot. It's been fun, and I think I'll see you next week. So thanks for your attention, and bye bye.